All right, so the next thing that I want to say to you, which is massively useful for physics, uh, is the Taylor series. So I'm not going to derive the Taylor series, but it is that the function, any function of x, is equal to this equation down here. That it's equal to this sum of derivatives of the function times x minus x naught to the uh, nth power uh, over 1 over n to the factorial. So this, I accidentally forgot something to write something here, but it's the derivative at some initial point. So it's the function at some initial point times the derivative of at that point times x minus x naught. So that gives us a pretty good approximation of what the value should of f of x should be for a small value of x minus x naught. But to get better approximation, you get 1 over 2 times 1, uh, which is d times d squared f ddx squared at that initial position times x minus x naught squared, plus 1 over 6 d cubed f dx squared cubed times x minus x naught cubed, and so on and so forth for infinity. And if you do that for an infinity number of cases, it doesn't just become a general, it doesn't just look like a generally good uh, approximation where all of the units check out and everything like that. It is exactly equal to the initial function. So this equation gives us the Taylor series. So for example, I did the Taylor series for a number of simple equations that I'm going to get to why I did it for them in a second. But e to the x equals f of 0, e to the x of 0, uh, which is just e to the 0 plus 1 over 1, uh, the derivative of e to the x at x equals 0, which is again e to the 0 times x, plus 1 over 2 factorial e to the 0 times x squared, plus 1 over 3 factorial e to the 0 times x cubed, which ends up just being 1 plus x squared plus x cubed over 6 plus dot dot dot. Uh, then you do it with sine of x, and that's going to be a little harder to do because sine of x is derivative is not just itself, it's a cosine. But as you keep on taking these derivatives, it's going to end up alternating between sines and cosines. And then if you look at the initial position, the initial x, and take that to be 0, then all of the sines are going to be knocked out and all of the cosines are going to stay. So you get a function of x minus 1 over 6 x cubed plus dot dot dot. Cosine of x is similar, except for you get 1 minus 1 half x squared and dot 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 and so on. So uh, the best justification that I can come up with for why Taylor series work is because if you take the derivative of a Taylor series, it just becomes the Taylor series of the derivative. So f prime of x equals 0 plus uh, f prime or df dx times 1 plus d squared f dx squared times x minus x naught because you take the derivative of x minus x naught squared, and that gives you 2 times x minus x naught, which cancels out the 2 in front of the d squared f dx squared, plus 1/2 d cubed f dx squared times x minus x naught squared plus dot dot dot. So if you look at this, this is actually equal to f prime of x naught, and then this is all at x naught, at the area f x naught. This is equal to f prime of x naught plus d dx f prime of x naught times x minus x naught plus 1/2 d squared dx squared f prime of x naught x minus x naught squared, which if you look at it, you'll realize is just the Taylor series for the derivative of the function. So instead of having the initial function be, if you take the derivative of the initial function and the initial Taylor series, it becomes the Taylor series for the derivative. So it becomes the derivative times at position x naught plus the derivative of the derivative times x minus x naught plus 1/2 the double derivative of the derivative times x minus x naught squared. So it is just the function that you want to see. It is just the function that you were looking for. So basically just take the derivative of a Taylor series and it should give you the Taylor series for the derivative. So that is all well and good, and that's going to be, I find that to be an easier way to understand kinematics equations than what we go through with the algebra, but that is because I've gotten used to it, and I will probably include both ways to do it if you want to. What is more interesting to me is something called Euler's equation, which is the equation that e to the ix is equal to sine or cosine of x plus I sine of x. So this is not immediately obvious why, but I think a good way to think about it is just that you know that the derivative of an exponential refers to is proportional to itself, and you know that the double derivative of a cosine or a sine refers to itself. So it makes sense that this exponential should be in some way related to the cosine or sine. And the way that we generally prove this is by using, it's not actually a proof, and mathematicians will get mad at me for saying it's a proof, but the way we generally prove this is by taking the Taylor series for 1 plus ix plus ix squared over 2 plus ix cubed over 6 plus dot dot dot, and seeing that that is equal to 1 plus ix minus x squared over 2 minus ix cubed over 6 plus dot dot dot, which is going to be equal to cosine of x plus I sine of x's Taylor series. So when you set these two Taylor series equal to each other, you get first 1 plus I for the first 1 plus ix for the first terms plus minus 1/2 x squared minus plus ix cubed for the second term plus dot dot dot. And what you see is that, oh, and I forgot a 6 here. But what you see is that they are exactly coinciding with each other. So the Taylor series for e to the ix is exactly equal to the Taylor series for cosine of x plus I sine of x. The reason that this is useful is because sines and cosines are difficult to work with when you're working with differential equations, which are equations where, as I said, the sine and the cosine or the derivative of something is in some way a function of the original function of the original value. So if that's the case, then e to the ix is a much better way to a much better thing to do equations out of. And it also once we've done those equations, once we've understood what's going on, we can convert it from e to the ix from like some imaginary value back to a real value and use that for our final equations. And it also helps kind of with one thing that you're going to do very late in the class, which is damped harmonic oscillators, where you end up finding the cosine of an imaginary number. And because you found the cosine of an imaginary number, that means that it's going to just be some exponential number, because each of the ix, each of the I times t, let's say, would be cosine of I times t plus I sine I times t. So you can tell what's happening when you start getting imaginary numbers. It allows you to solve differential equations more. So that is getting quite ahead of ourselves, and we're not going to be using it exclusively, but if you go into physics and if you go into greater courses, then this is definitely a useful course. I remember that I had to use this in my equivalent of 201B or 202, I think. So thank you for looking at this, and then the next video is going to actually describe stuff that's in the textbook and describe physics instead of just math. Thank you very much.